Swayam Prabha. Digital India. Educated India.
Welcome back to Aircraft Structures 1 course, and this is Professor Anup Ghosh from Aerospace Engineering Department, IIT Kharagpur. We are at the first lecture of the module 8 in sequence. This is the 38th lecture, and we will attempt the problem of torsion in theory of elasticity approach. So, in that connection, first thing what we get is the recapitulation slide. In this recapitulation slide, we have covered history of solid mechanics or structural analysis, starting from the beam analysis, then how before the beam analysis, how the theory of elasticity came in, how the linear material, nonlinear materials are described, and then to beam analysis, plate analysis, vibrations, who did what, all those things we have learned, and we have seen that the development is still going on. Most recent development may be in the area of cell analysis, which is very important structure while we try to analyze aircraft structure, where all the members probably are curved in nature and thin in dimension in the lateral direction. So, it belongs to the cell group. After that, what we have learned is that how an aircraft experiences load, or how does it withstand load, where from the loads come. In case of aerodynamic loads, there are different conditions like rolling, pitching, or normal aerodynamic lift load, or maybe gust, or maybe an engine out condition from propulsion side. All those loads, where and how it comes, we have discussed so far to some extent. We have also seen different type of aircraft structures, how those are fabricated, how does they look like, how do they look like, and then we have seen different types of loading envelope, flight envelope. A new concept is applied for different types of aircraft, how the inertia load plays a big role, and we see that that for civil aircraft, where the maximum G force or inertia loads may be limited to up to 2.8 to 3.5, or maybe approximately said as 3, but whereas in case of aerobatic aircrafts or a fighter aircraft, it goes to maybe 5.5 or 6 G. So, it is a huge amount of change of force we need to take care. So, depending upon the type of aircraft, we need to develop the flight envelope, and we need to consider the parts of the structures to design to withstand those inertia loads. Not only inertia loads, it also experiences many other loads, as we have discussed. We have seen the bending moment shear force diagram of whole aircraft divided in two parts in orthogonal direction, that is fuselage and wing, and then shear force bending moment we have done. We have done three dimensional truss, solved problem of landing gear, and then we have gone to the theory of elasticity. But before we go to the theory of elasticity, we have solved problems related to deflection, to find out deflection. Different energy methods we have learned, and in the amongst the energy method, a very important method we have learned, that is the Rayleigh-Ridge method. So, with that note, we went further for theory of elasticity, we developed several equations, 15 equations namely maybe and more, because compatibility is also involved there. We have seen compatibility in terms of strain, we have seen compatibility in terms of stresses. Compatibility is something which has to be maintained within a structure while we define in mathematical way. In practical world, all structures are continuous, there is no problem, but while we define it mathematically, we need to define accordingly. And after that, solving a few problems, initial small problems with inverse and semi inverse approach, we have come across to the problem where we have discussed the effect of a circular hole in a plate which is uniaxially loaded, and we have seen that there is a huge stress concentration because of those loads may be observed, that is up to the 3 times of the tension applied, and that is the reason the crack opens transverse to the direction of the application of the tensile stress. We have seen how we need to take care of the holes by reinforcement. We have seen how a crack propagation takes place and why it is like that with help of ellipse and stress concentration equations. So, after that we will try to solve this week, we will start to solve this week problems related to torsion. Torsion problems what you have solved in your previous mechanics course probably is little bit different than the way it will be approached in this section. The basic difference is the considerations of warping. What is warping? That is a big question. While there is out of plane displacement, out of plane means which plane we are talking about. So, if we consider in most of the cases what you have seen is that we have considered a cylindrical shaft which is fixed here, and we applied some torsion T, and what we say we have observed or assumed that if we consider any of one of these plane, that plane remains at that plane, but it rotates, but there is no displacement in this direction. That is what we said as out of plane displacement. So, out of plane from the plane of the cross section of the circular member. So, if there is some displacement out of plane, we call that as a warping. Warping is a phenomena we need to learn, because practically if we do, if it is a non-circular section, we observe a warping very predominant way. For example, if we consider a rectangular bar, what will happen if we apply a torsion? This will deform like this. And this will continue for all sections. I have exaggerated the thing. It is difficult to draw all the portions, but this out of plane, this corner is coming down and the other two corners are going up. This type of phenomena is known as the warping. So, if it is a non-circular section, we need to take care of that, and how do we take care that is first established or developed by Prandtls, and those assumptions the way it has been done, that we will learn slowly. in a very small segments of small lectures. So, let us proceed with that note. So, what do we see? The torsion problem. The well known torsional equations for circular shaft, solid or hollow, is tau shear stress developed is T r by j, and the theta per rotation per unit length, twist, angle of twist or rotation per unit length is where T is the applied torsional moment and J is the polar moment of the cross section. As I said, Saint-Venant started the analysis and then later Prandtl also worked on it. In this approach to the torsion problems, following assumptions are made. The body is cylindrical. Do not think that cylindrical means a circular cross section. The body is cylindrical with the axis lying along the z axis. Axis system we will see in the next page. We have drawing for displacement equations, we will see. The unit angle of twist theta is constant along z axis. Here comes the most important assumption. The projections of the cross of sections of xy plane rotates as rigid bodies. Earlier we did not use this term projections, we said that the sections on the xy plane rotates as rigid bodies. So, that is the difference. Here we say the projections of this. So, with that considerations we will go. So, if a particular section is projected on the xy plane, that rotates as a rigid body, not the section completely. So, there is out of plane deformation and we need to take care of that. So, let us try to define the displacement first with respect to torsion. In this section, it is the description of the problem first. This assumption restricts the problem to the torsion of a cylindrical body with no axial restraint at the ends. Why it says like that? Let us read and we will come back again. There are essentially two limiting torsional problems, namely that of free torsion, in which the cross sections are free to warp. Please note that in case of free torsion, sections are free to warp or free to deform out of plane with respect to the xy plane, and that is restraint torsion, and that of restraint torsion in which at least one cross section, usually at one end of the cylinder, is constrained to remain parallel to the xy plane. So, here what we are considering, that no plane is restrained. Even the case we discussed for the circular, the figure I have drawn in the last slide, it is not like that. No part, even this plane as well as also this plane, no plane is restricted to deform out of the plane or the xy plane. Here with respect to the xy, it is quite clear. The analysis that follows will therefore be the free torsion problem. So, what we will consider in this particular case is for the free torsion. So, that for the free torsion, how are we going to define the displacement and how do we get the first starting equation? With that small note, we will end today's lecture. So, let us try to go forward. Here we have it. So, initially this section, this is the section of the cylindrical body, bottom section, this dotted one is the top section, and then there is a torsional force applied on this body, and we have seen that theta is the rotation per unit length. So, the total rotation here is theta multiplied by z, because from this point to this point or the segment of the cylinder cylindrical body we are considering is the of length z. Now, with that considerations, considering x y is like this, similarly x y is also here at this plane, we are considering the displacement at this particular point. We define that a point P, which is r distance apart from the axis or the z axis, is rotated to P prime. Here both are P prime, because initially this was the P prime point, and then after rotation, after application of the torsion, it has rotated to this point. Now, with this concept how do we get the displacement and other equations, let us try to see. Plane containing P prime is rotated with respect to the plane containing P with application of a torsional moment. Now, u is equals to r theta z sin alpha and v is equals to r theta z cos alpha. This is not derived here, why the minus is coming, why it is not like that. I would suggest you to do this as homework, because if we go for the geometric way, drawing the components and other things, it becomes difficult to understand. So, we need to find u v, as we have discussed that finding u and v in geometric way is much more difficult. So, following trigonometric approach probably will help. So, what we can assume that as it is the drawing what is prevailing here, we will draw the same thing, same phenomena in a different way. So, this is the x y plane, and with r, I think I need to revise it. Say this is the point represented as x 1 y 1, and after, and this is the angle alpha, and after rotation it goes somewhere here, which is x 2 y 2. Now, this is theta z. Say if we simply consider u, u is equals to r cos alpha minus r cos theta z plus alpha. So, if you simply do it, you will get this relation, and similarly V also you can find out. So, with that I think we can proceed, you can solve this easily. So, what do we have, since we have the other relations like x is equals to r cos alpha and y is equals to r sin alpha, u becomes minus of y theta z and v becomes x theta z. Z is not subscript, please be careful, z is never subscript. So, that is what is written here repeatedly, and we define one more important function w, function of x y. This function is the difference with respect to our previous things. From the stress strain relation, this is known as the warping function. From the stress strain relations and strain displacement deformation relations, we get this. This will be repeated in next slide also. We will use it, sigma x, sigma y, and all those. Will let us see how do we come to the equilibrium equation. So, with this note, what we see is that we have all the 6 components of stresses here, and if we substitute these values, what we have got the displacement because of the torsion. If we substitute all those values here, we finally get that sigma x, sigma y, sigma z, and tau x y is equals to 0. You can easily substitute this and check. I have checked several times. Please note that this a and b are written in a generic form, which are function of alpha e and nu. E and mu is the is expressed in terms of E and mu. Then tau I z and tau x z are the 2 remaining stress components, and if we substitute these values here, what do we get? We get this is a simple substitution. In this we get that tau I z equals to z x theta plus del w del y, and tau y z is this, tau x z is g del w del x minus y theta. So, 1, 2, 3 are the 3 equations. In case of free torsion problem, W is obtained from equilibrium conditions. Equilibrium condition without any body force, which is the third equilibrium condition we need to bring, because all other terms are 0. Only this equation will lead to a equation what is useful. So, simple substitution of that here, what do we get is that we get a function in terms of w, and which may be stated as that grad square w is equals to 0. So, for a torsion problem to solve, our equilibrium equation is grad square w or the working function is equals to 0. So, with that note, let us stop here for the development of torsional problem. We will come back in the next lecture with a few more concept, and we will go through it. So, we come to the standard references what we need to follow, and what we have learned or initiated is the torsion problem as the theory of elasticity approach. And at the end, I thank you for attending this lecture, and we will come back with some more lectures soon. Thank you.